we were talking about shear force and bending moment because we want to eventually get to stress. Okay. So let's say that there's a beam. Subjected to some load, and it could be any fancy load. We basically cut the beam at some section because maybe perhaps we are interested in finding the, we know that if it fails, it will fail at that particular point because maybe there's a defect there, or maybe there's a weld, or maybe there is some attachment which connects the left side with the right side. And so we want to basically find the shear force and bending moment diagram there. And that's what we did so far. V M, and we drew this curve, E of X, M of X. So what we'll be exploring in this chapter is how the shear force leads to shear stress. Okay, and we denote shear stress by tau. Okay, so shear stress, think of shear stress as something which makes one object slide over the other. And then the bending moment M, it leads to normal stress. And this is kind of less intuitive, and let me explain this. We denote a normal stress by sigma. When you think of normal stress, you think of axial, well, you take a rod and then you load it with P, then you say that the shear stress is P divided by A, right? So this is one way to get stress. There's a stress acting along the cross section and it leads to a stress. Turns out that bending also leads to a normal stress. Okay, and this is how you can think about it. So if you take a beam, okay, and then apply a moment. Now let's apply a moment on both sides, sort of bending it. So this is due to an equal and opposite bending load. So our intuition tells us that depending on the shape of the beam, the shape the beam takes, one part of the beam is going to be under compression. And it's going to be under compression. The top part is going to be under compression. As you can see that if this is the length of the beam, the top part is going to have a length less than L just by looking at it, right? Similarly, the bottom part is going to be under tension. Because the length of the bottom part is greater than L. Now, I think that once you have this understanding, you can see that this is nothing but a tension specimen. It's subject to tension, right? It's going to elongate. Similarly, bending moment has caused the tension in the lower half. So the bottom part is going to be under tension. And that's why bending moment M leads to tension. Just like tension, we could have a scenario where we could take this beam or this axial rod and subject it to compression. In this case, the stress is again P divided by A, but it will be negative P divided by A because P is acting so as to decrease the length of the axial rod. So this is an example of compression. But then we also have compression in the top half because the length of the top half is decreasing. So that's how intuitively you can make sense of how a moment M will lead to normal stress, sigma. In fact, it will always accompany with a compression on the top half. Of course, this depends on how M is applied. If it's applied the way I've shown, the top part is always under compression, the bottom part is under tension. If you change the direction of M to be the other way, you'll have exactly reversed effect. The top part would be in tension, lower part will be compression. So this is, I think, less intuitive, but hopefully I've convinced you that it's possible to have normal stress with M. Okay, so both of these you have units of Newton per meter square. Or this is an SI. And there's the other unit is FPS. The units are pounds per square inch. Pounds per square inch, or PSI. You probably recognize PSI as a unit of pressure, but pressure is also units of stress, right? Force per unit area.
I'm sorry, what letters?
Sigma. Let me write it down. Tau. Sigma. We're learning more Greek letters with this, with the virus, COVID, right? I think Omicron is 26. It's a number in Greek letters. Okay, so next part, let's talk about Cartesian stresses. Okay, so let's take a thin plate. This is just introducing the notation for Cartesian stresses. X, Y, just not write it there. I'll reserve this for something else. Let me draw this. It's still there, but let me draw the axis on the right side. X, Y, and Z. So when this thin plate is subject to a loading, we can have three stresses on this. We could have a shear stress. Now note that shear stress always acts as a sliding stress. So it could slide along the x-axis, it could slide along the y-axis. There's only two ways it can slide. So we would have a stress tau Z Y. Again, I'll tell you why I wrote ZY, not YZ. And then tau, oh, I made a mistake. This should be tau ZX because of the X direction, and then tau ZY. Two directions, right? And then for the vertical one, that's because that's the stress which is acting normal to the surface. So it has to be called as sigma. I'll call it sigma Z. So sigma is the normal stress, tau, as I said, is the shear stress. And we use this convention tau I j, right? For the shear stress. For sigma Z, it's kind of obvious. It's normal to, it's along the Z direction, so we put sigma Z. But what about tau ij? How do we decode I and j? The first index I is always normal to the plane. And the second index gives me the direction of the shear force. So to interpret that here, I wrote tau Zx. That is because this plane surface has a normal in the Z direction. Right, Z is pointing upwards. And then I put X here because it acts along X direction. So following that notation. So that's the notation we'll follow, and that's kind of universal. Okay, now there is so in general, if you have now I drew the plate in a perspective, but if I draw orthogonal view of it, this sigma x, sigma x, sigma y, sigma y. Tau, okay, let's draw this first. X, y. So when I show this arrow, I need to use the first index to indicate the normal to this plane. The normal to that plane is x, and it's pointing in the y direction, so tau x, y. And this one would be tau. First index is normal. The normal is along the y, so y. First index, and the second index is going to be the direction which the shear stress acts. In this case, it acts along x. Okay, so you can do the same thing here. Tau yx, tau xy. Okay, so what I've shown here is actually known as a plane stress element. Stress element, and this is the one which we'll be using throughout the course. In fact, what we'll do is when we have a general 3D object, we'll look at plane stresses for one plane, xy plane, xz plane, yz plane, and that's how we'll be analyzing things. Now there is this thing which is if you do moment equilibrium about O, that is you take moments about O. So when you take moments about O, you can show that one can show that tau xy equals tau yx. I mean, you can just observe that, right? If you take moments about O, tau xy, the tau x on the right side, tau x on the left side rotates the element counterclockwise, but tau yx on both sides rotates it clockwise, but it's not going to actually be rotating. So to ensure equilibrium, those forces should be equal, which means that the shear stresses should be equal. And then so tau xy equals tau xy. This is known as complementary shear. Tau xy always ensures that tau yx is equal to tau xy, and thus for plane stress, we only need three numbers: sigma x, sigma y, and tau xy, because tau xy equals tau yx. So whenever we talk about plane stress, we only look at three stresses: two normal stresses, one shear stress, because they're always equal. So let's talk a little bit about strain. So what the stress sigma in this is a normal strain. So we are in 3.8 elastic strain. So assume a rod subject to a load P. Let's say the length of the rod is L. Because P is substantially big, what you'll see is that this rod extends by a length, let's call it delta L. So elastic strain is defined by this Greek letter epsilon, and in this case, let's say that this is our x-axis. The elastic strain in the x direction would be, the definition is change in length divided by original length. So in this case, the change in length is delta L divided by L. And then if you want to find the stress, given the strain, we need to know what the Young's modulus is, which is E times epsilon x, where E is Young's modulus. Okay, that's a constant for the particular material. Different material will have a different elastic modulus. Okay, now the interesting thing here is that if you stretch something in the x direction, what you'd expect is that, when you can see this, that if the length increases in one direction, and since the volume of the material cannot change, it actually begins to shrink in the y direction and the z direction. So a strain in the x direction causes a strain in the y and z directions, other directions. So that strain EY is given by the Poisson's ratio. I wonder what it's called mu maybe, times EX or epsilon x, and EZ is going to be the Poisson's ratio times EX, where this symbol is the Poisson's. Yeah, please. Oh, thank you. Okay, that's also material constant. So there is a foam which actually has a negative Poisson's ratio, which is kind of interesting, which is if you stretch it in one direction, it also expands in the y and z direction. So you can actually search for materials with negative Poisson's ratio. They're kind of interesting. They defy our understanding of how normal materials behave. Okay, so that was just telling you what happens in one dimensional. So stress in X leads to strain in Y and Z. Note that the stress in the Y and the Z direction is still zero. So we can generalize this to a 3D stress. What if the element is subject to stress in the X, Y, Z direction? What will that induce? So I'm going to just generalize this. So I looked at a 1D case, but let's look at a 3D case where there is stress in all three directions. And there will be an equivalent stress in the other side, sigma x, sigma y, sigma x. So if you have stresses in all directions, then the strain is going to be, well, sigma x divided by E. We know that that's the strain due to the normal stress sigma x. But because it's also being stretched in the y and z direction, you will see that there's a strain due to the effect of sigma y and sigma z. Sigma y and sigma z will create a strain, but that would be multiplied with the Poisson's ratio. So a better way of writing this is perhaps pull things out, E, and then sigma x minus mu sigma y plus sigma z.
Is there a reason you think lowercase
Lowercase delta. Oh, I'm really bad at writing this. Yeah, sigma x plus sigma y. Everything here is sigma. Sorry about that.
So when you were describing that extra sigma?
Yes, everything so far has been sigma. The only thing which is, I guess, different is delta, if that's leading to calculus. This is the only thing.
Right, okay.
Yeah. And then over here. So your homework problem, which will come in the next homework, as I said, will involve this. You need to find the strains due to stresses in all three dimensions. Oh, I think it was 2 dimensions. Okay, so similar to normal strain, there is shear stress and shear strain. Shear strain. So this is, if you start off with a sort of a rectangle and you load it with a shear stress, now what will happen is this is now sliding, so it's going to cause this rectangular piece to be shaped like a parallelogram. And of course, this part is clearly it's fixed to the or grounded, right? So it cannot change its position, but it will simply change its shape. So this angle here is, let's call that gamma. And then gamma is the shear strain. And there's a formula for gamma. It is gamma, which is the shear strain, is tau, the shear stress, divided by G, where G is called the, just like Young's modulus, G is a material constant, called the modulus of rigidity or shear modulus. So it turns out that the Young's modulus, the shear modulus, and the Poisson's ratio are all related. And it is basically a derivation which you can find in some book, but it's not very important here. We just need to have the expression. So E is G equals to 2G times 1 plus mu, Poisson's ratio. That's how the three are related. So you only need to know two of the three in order to find the third one, right? So if you know E and nu, which is usually easier to measure, then you can find G. And then once you know G, you can find the shear strain by knowing the shear stress.